Good morning, good afternoon, whenever you're watching this. My name is Victoria, and I'm going to be presenting the stereoselective synthesis of dimethyl-4S ally N-boc-L-glutamate and related conjugures reaction. I just want to first start off by saying I'm sorry if I cannot pronounce words right. I'm going to be trying my best, but I'm sure here and there I will be pronouncing some words wrong. So we're going to start off by talking about the reaction. So this reaction starts with S-dimethyl 2-terdeoxycarbonylamino pentane dionate, which is seen on the left. And once it's mixed with LiHMDS THF negative 78 Celsius and alanide bromine at negative 78 Celsius, you will get the final product, which is our dimethyl 4S 2S 2-ally 4-terdeoxycarbonylamino pentane dionate. The scale and optimization. The first question is it expensive? So this reaction requires a lot of different components to it, as the article did not state whether this was an expensive reaction or not. Based on the information given, I would say it is an expensive reaction. My reasoning for that is that there are several elements involved that had to be purchased, along with different components needed as well. The second question is how large of a scale can the reaction run safely? Again, the article did not state that, but to me, this seemed like a pretty big reaction. I would say it can't be too bigger, as I don't think it would run safely if it was much bigger than what it is now, just because it is a pretty big reaction. The checking process. Did the checker make any additional comments? No, the checker did not in the paper. Did the checker make any contributions? Yes, the checker did. In the notes section, it was noted that the checkers purchased a lot of the material used for this procedure, which we will discuss later on. The reaction apparatus. So on the right side of the screen, I put a picture of the assembled reaction apparatus. So it is a 250 milliliter 3-necked round bottom flask with 1423, 1926, and 1423 ground glass joints equipped with a Teflon coated magnetic stir bar. Then there was a second reaction apparatus, but this was not pictured in the reaction workup. It is a flask fitted with a vacuum adapter, 1423 round glass joints that is connected to a double manifold, while the other two necks are stoppered with glass stoppers, 1926 and 1423 ground glass joints. So reagents and starting material. The most important one is our S-dimethyl 2-terdeoxycarbonylamino pentane dionate. This is our biggest reagent that we will need. And then we will have LiHMDS, anhydrous Na2SO4, ethyl acetate / hexanes, and anhydrous tetrahydrofuran. Now the reaction procedure. It is a bit long, so bear with me. So the first step is the oven-dried 250 milliliter 3-necked round bottom flask, seen in the previous slide, was charged with S-dimethyl 2-terdeoxycarbonylamino pentane dionate. It was 3 grams, 10.9 millimoles when equivalents. The second step was the flask was fitted with the vacuum adapter and then evacuated and refilled with argon 3 times. In the third step, under a flow of argon, the center 1926 glass stopper was replaced by a rubber septum, which is pierced with a 21 needle connected to the argon line and an 18 needle connected to an oil bubbler. In step 4, I put a picture to the left, as you can see it all set up, but the other 1423 glass stopper was replaced under argon by a glass thermometer adapter fitted with a lower temperature thermometer. Step 5, anhydrous tetrahydrofuran, 45 milliliters, 0.24 moles, is added 1 portion at room temperature via a plastic syringe fitted with an 18-gram needle through the rubber septum under argon. Step 6, the flask was cooled to negative 78 Celsius using a dry ice acetone bath in a Dewar flask. I put a picture of that to the right. Next is step 7. After 10 minutes, a solution of lithium bitrimethylsilamine, 1 mole in THF, which is 24 milliliters, 24 millimoles, 2.2 equivalents, was added dropwise via a plastic syringe fitted with an 18G needle over the course of 25 minutes under a flow of argon. Step 8. The rate of addition of LiHMDS solution was such that the internal temperature of the reaction mixture maintained at negative 78 Celsius. So I feel like this was a big step in the procedure just because over and over again you will see that the temperature is maintained at negative 78 Celsius for a while during the procedure. So step 9, after stirring the pale yellow solution for 30 minutes at negative 78 Celsius, alide bromine, 2.8 milliliters, 32 millimoles, 3 equivalents was added dropwise via a plastic syringe fitted with a 21G needle over 12 minutes under an argon atmosphere. Reaction procedure continues. So step 10, the internal temperature of the reaction mixture was maintained at negative 78 Celsius during the addition of the alide bromine. Then step 11, the pale yellow reaction mixture was stirred at negative 78 Celsius for an additional 2.5 hours. During this period, the internal temperature was maintained at 78 Celsius by periodic addition of dry ice to the bath. So like I stated before, it's always, for a while, this temperature is maintained at negative 78 Celsius. Step 12. After 2.5 hours at negative 78 Celsius and completion of the reaction was confirmed by TLC analysis, which I put a picture of the TLC analysis on the bottom. The reaction mixture was quenched by the addition of saturated aqueous ammonium chloride solution, 30 mL. Step 13, the dry ice acetone bath was removed and the reaction mixture was allowed to warm to room temperature over the course of about 45 minutes. So you could see that in the picture below. Step 14, the contents of the flask were then transferred to a 500 ml separatory funnel, which again is seen to the left. Step 15, the phases were separated and the aqueous phase was back extracted with ethyl acetate 3 times 60 mL, and the combined organic phases were washed with brine 20 mL. So this is, again, pictured to the right. This is the last of the reaction procedure. So step 16, the crude mixture was dried for 10 minutes over anhydrous Na2SO4, 10 grams, filtered through a fritted Buchner funnel under house vacuum, 75 mmHgs, and then filtrated, was concentrated by rotary evaporation, 36 Celsius, 30 mHgs, followed by high vacuum, 20 Celsius and less than 1 mmHgs for 30 minutes to afford the crude mixture of colorless oil, as you could see below. Step 17, a glass chromatography column was charged with silica gel and was dry packed, eluting with 5% ethyl acetate hexanes until the resulting silica column was a homogeneous and cool to touch. Okay, so step 18, the crude oil was dissolved in CH2Cl, then the silica gel was added and the solvent was evaporated by high vacuum for 30 minutes. Step 19, the absorbed silica gel was loaded onto the column, followed by a layer of sand. The packed column was eluted with 300 mL of 5% ethyl acetate hexanes, then 2,000 milliliters of 10% ethyl acetate hexanes, followed by 800 milliliters of 20% ethyl acetate hexanes. The elutes were collected in a 25 times 18 mm test tubes totaling 47 fractions. And the last step of this procedure was the fractions were contained only one compound were combined. The fractions containing only one compound were combined and concentrated under reduced pressure on a rotary evaporator, followed by a high vacuum to afford compound as a colorless oil. Now, the reaction workup. So, the 3-necked round bottom flask containing a Teflon-coated egg magnetic stir bar was dried in an oven for 16 hours at 105 Celsius. S-dimethyl-2-terboxycarbonylamino pentane was obtained from the AK Scientific as a white solid and used as received. The checkers purchased 2-terboxycarbonylamino more than 98% from TCI and used as received. This is where I'm going to be talking about what the checkers contributed. As you can see, the checkers will be purchasing a lot of stuff, like I said previously. So the checkers purchased HPLC grade tetrahydrofuran from RCL LabScan and passed it through a drying aluminum column and PureSolve MD5 solvent purification system before use. The submitters use a anhydrous tetrafuran obtained by distilled dry tetrafuran taken from MBSPS over sodium in the presence of benzophenone and collecting it with this distillation trap, as you can see in the picture to the right. The Dewar flask was purchased from Hope Scientific Limited. The checkers purchased the Dewar flask from Conquin Synthware Glass. Lithium trimethylsilamine 1 mole in THF in assured sil bottle was purchased from Sigma Aldrich as a light yellow liquid and used as received. It was taken up from the Sure Seal bottle via syringe under a positive pressure of argons. The checkers purchased lithium trimethylsilamine 1 mole in THF from Shanghai Macklin Biochemical Co., which was used as received. The allied bromide was purchased from Sigma Aldrich as a colorless liquid used as received. The allied bromide was taken up from the amber colored bottle via syringe under a flow of argon. The checkers purchased allied bromide from Shanghai Allied Biochem, which was used as received. The checkers purchased ammonium chloride from Deckerman, Hong Kong Chemical Industry, which was used as received to prepare the saturated ammonium chloride aqueous solution. The checkers purchased sodium chloride, AR grade from Deckerman, Hong Kong Chemical Industry Ltd, which used as received. The checkers purchased sodium sulfate, anhydrous, AR grade from Deckerman, which was used as received. The checkers used a medium porosity freighted Buchener funnel with capacity of 150 ml, and the checkers purchased silica gel from Merck, which was used as received. The checkers purchased hexanes GR grade with ethyl acetate from Duxan Pure Chemicals, which was used as received. The checkers purchased GR grade diachloromethane from RCI LabScan, and thin layer chromatography TLC on silica gel 60 F254 aluminum TLC plate eluting 25% VV ethyl acetate hexane showing fractions 1 to 4 from chromatography, as you can see in the picture below, which is provided by the checkers. Next, we're going to be talking about purification. So the submitters purified the crude material by a flask column chromatography and isolated 2.9 grams of pure dimethyl 2S4S2Li 4-terabioxycarbonylamino pentane. Also isolated 65 milligrams of dimethyl 2S4S2Li 4-terboxycarbonylamino pentane and side product, and 203 milligrams of pure side product as pale yellow oil, as you can see in the picture to the right. So these are just some proofs of purification. So this is the HNMR spectrum of dimethyl 4S2Li 4-terboxycarbonylamino pentane. This is the 13C NMR spectrum of 2S4S2Li 4-terboxycarbonylamino pentane. This is the 1H NMR spectrum of the dimethyl 2s 4s 2-ally 4-terabioxy carbonyl amino pentane dionate. And here you could see that they calculated the molar ratio and how they calculated it. Here is the 1H NMR spectrum of dimethyl 2s 4s 2-ally 4s N-terabioxy carbonyl 4-terabioxy carbonyl amino 5-methoxy 5-oxypentane amido pentane dionate. And this is the 13C NMR spectrum of dimethyl 2s 4s 2-ally 4s N-terabioxy carbonyl 4-terabioxy carbonyl amino 5-methoxy 5-oxypentane amido pentane dionate. So proof of purification. So the submitters separated by flash column chromatography 65 milligrams of compound 2 and side product 3, which were attained by the mixture fractions in the first chromatographic purification. They used a glass chromatography column with an inner diameter of 2 centimeters and 5 centimeters of silica gel, and the column was eluted with 50 milligrams of 6% ethyl acetate and hexane, 50 milliliters of 8% ethyl acetate and hexane, then by 200 milliliters of 10% ethyl acetate and hexane. The elute was collected in 13 by 100 mm test tubes in 35 fractions. Fractions 11 to 18 contained pure compound 2, which were concentrated by rotary evaporation and then under high vacuum for 30 minutes to obtain 20 milligrams per for a total yield of 2.94 grams, which is 86% of compound 2. Fraction 20 to 33 were concentrated by rotary evaporation, then under high vacuum for 30 minutes to produce 37 milligrams of pure side product 3 for a total yield of 240 milligrams, which is 4%. Again, this is proof of purification through TLC, so thin layer chromatography on a silica gel from the column chromatography of a mixture of product 2 and minor side product 3. So this picture was submitted by the submitters. So some safety note and hazard warning. So for this procedure, there had to be evaluations with how different things would react with S-dimethyl. So some of those things that they had to risk assess were 2-terabioxy carbonyl amino pentane dionate, tetrahydrofuran, acetone, dry ice, lithium bis-trimethylsilamine, allied bromide, amino chloride, ethyl acetate, hexanes, dichloromethane, sodium sulfate, silica gel, and denaturate chloroform. Now the discussion. The excitatory synapse of the mammalian CNS release glutamate acid as a chemical messenger. Several CNS-related acute and chronic neurogenetic disorders have been associated with the excessive activation of glutamate receptors. In order to describe the roles of different glutamate receptors, several conformality-constrained glutamate derivatives have been synthesized and tested for neurotropic activity. It has been known that the treatment of N-trial-L-glutamate dimethyl ester with a non-nucleophilic base such as LDA will generate corresponding lithium enolate from the distill ester, which can be reacted with benzyl chloroformate. Extension of the reaction of N,9-phenylchloroenyl L-glutamate diesters to include a variety of alkyl halides was reported by Rapport and Koshkian. North reported that the treatment of the lithium diene of N-CBZ L-glutamate diesters with the allied bromine or methyl iodine led to 1:1 and 2:2 mixture, respectively, of 4-ally and 4-methyl glutamate. Zhu reported that methylation of the dianolate of N,P-nitrobenzyl dimethyl N-glutamate with methyl iodine afforded with 4-methylated glutamate with high anti-selectivity. The divergence of diastereoselectives of the addition in reported cases may be contributed to subtle effects of the N substitutes and reaction conditions. Following their studies on the anti-selective hydroxylation of the lithium dialane of dimethyl N-CBS L-glutamate with Davis reagent, which is 3-phenyl N-phenyl sulfaphenyloxyrenidine, I believe. Hannessine and Margarita reported the corresponding anti-selective hydroxylation of dimethyl N-Bach and L-glutamate in absence of any additive. The high anti-selectivity was rationalized by a proposed transition state involving a lithium-coordinated 1,3 dynamic intermediate with Z0 type analyte geometry. So this is a figure below, which is the possible transition states for models of high anti-selectivity. The Hannessine protocol, starting with L-glutamate acid for the synthesis of dimethyl 4S aldehyde N-Bach L-glutamate, has been used in the context of the development of medically important compounds as well as the total synthesis of complex natural products. They've reported a revised procedure for the gram scale synthesis of dimethyl 2S4S 2-allyl 4-terpioxy carbonyl amino pentane dionate from dimethyl N-Bach L-glutamate using a high anti-selective alylation of the lithium dianolate. In the present version, they also isolated the self-condensed product 4% yield, which they had not reported in the original procedure. The formation of the byproduct varies with the reaction condition and increased when using 2.2 equivalents of LiHMDS, 3 equivalents of Ilg bromide, and stirring at negative 78 Celsius for 45 hours. Then NH4Cl, 2.3 equivalents of LiHMDS, 3 equivalents of allyl bromide, and stirring at negative 78 Celsius for 3 hours. Then NH4 chlorine. The experimental protocol was also applicable to the synthesis of N-CBZ analog as well as other 4 substituted derivatives of L-glutamate acid using methyl allyl bromide and sinyl bromide as electrodes fills. So this is just a picture of everything I discussed in the discussion part. So finally, meet the authors. So there were 3 authors of this. So you have Akash Misrar, who obtained his PhD in 2018 at Banaras Hindu University, and his current research involves asymmetric total synthesis of natural products, visible light, photoredox catalysts, and synthesis of biologically active compounds having medical importance. The second one is Stephen Hannessian. He holds the Ionis Pharmaceuticals and Server Senior Industrial Research Chair at the Université de Montréal. His research interest covers a wide cross-section of areas covering organic, bioorganic, and medical chemistry. And lastly, Quinn Hantio. She received her biology degree in the chemical technology with the Hong Kong Polytechnic University. She's currently in her 3rd year as a grad student at the University of Hong Kong, where she's currently studying cycloadditions in Professor Chu's laboratory. Thank you. If you have any questions, please let me know. I hope you enjoyed my presentation. And again, thank you.
Done.